So let's start with a simple setup. And I'm trying to draw this very carefully. And if I were you and you wanted to understand this, I would also, if I were you, try to draw this carefully. I'm trying to ensure a certain amount of symmetry. Excuse me? Yes. Yes. So I am trying to make a single loop motor core. That's what this is supposed to represent. And I'm drawing it in such a way that I can easily see an input wire and an output wire. But the core itself is the square portion of the wire, which is why I'm trying to draw it as symmetrically as I can. So I'm trying to ensure that this represents half the side length of a square. Is that all right? Thank you, Mr. Geisel. I appreciate it.
Yeah, no problem.
Now, I also want to draw this from another vantage point, and it might not be clear as to why I need to draw this vantage point, but I hope that it will be. I want to draw another version of it as if we were looking at it from this angle. Okay, so we would only see kind of a line, but I want to draw here and here kind of the wire coming in and out. So if the current was like I've drawn it in the picture on the left, then I would see, you know, if I was looking at it from the side, there'd be a current coming at me. So that little dot there represents a current coming at me in that wire. And then it would turn and there'd be a current going the other direction on the other side. And current would be going this way on the wire closest to me. And I can't see the wire that's furthest from me. Does that make sense? So everybody understand what I've drawn here? This is a square piece of wire. Yes, sir.
I was just kind of confused with the one on the right, like what the angle is. Is that the bottom?
I'm just going to try and find a piece of wire. That's what I'll have to do. I should have had a piece of wire here bending square. But if this was my wire, square, okay, if I was, can't do it. I can't do it. I should have just brought a piece of wire up here. I'll bend one in a minute, but I'm trying to say if I had, yeah, if this is my wire, I am turning it towards you and you're looking this way on it. So there's a wire on this side with the current coming this way, it turns, and the wire comes back this way. Does that make sense? So this represents the current coming this way, and that way, and then the actual thing would be like this, where the current's going this way, this way. Gotcha. Is that good for everybody? All right. Okay. So I think we can do this. Obviously, a current loop does nothing except for allow charges to pass through the loop. We want this to interact with a magnetic field. So I'm going to apply a magnetic field to the system, and I have lots of different magnetic fields we could attempt to use here. Some work better than others. So if I want to cause this loop of current to be turned by a magnetic field, I want to choose a magnetic field that would apply the right kind of forces to my system. So what I would like, and as I've drawn this, I hope you can see why I want it to work this way. I would like the loop to kind of turn this way or this way, meaning I would like this side maybe to go up or down and this side to go up or down so that I'm getting the wire loop to flip over. So I have choices on magnetic fields I can use to do that. I'm going to use a magnetic field this way. All right. So Hand rule. I'm going to draw in arrows to indicate the direction of the current on the four sides of my square. And I'm going to label this A, B, C, and D to indicate different line segments of my motor. So I'm going to look at the force on the portion of the wire from A to B, the force on the portion of the wire from B to C, C to D, and D back to A. Are we ready to go? Ready to go? So, right hand rule. And ignore this picture for a minute. Let's focus on this one. Current, magnetic field. My thumb points into the board. From A to B, there's a force into the board. Right? L cross B. So the force, which I will put in green, on the wire into the board. Are we all okay with that? All right. From B to C, no force. Do y'all see why that's true? Right, we don't define a plane. The direction of the current, the direction of the length and the direction of the magnetic field are parallel, which means they don't define a plane. So there is no force from B to C. C to D, I don't think I have to redo much. From C to D, it must be the opposite of A to B because the current's in the opposite direction. But if you use your right-hand rule, length is down, magnetic field is to the left. My thumb points out of the board, so there must be a force that way. D to A, they're anti-parallel, which means no force. So I clearly see that there's going to be opposite forces on either side of my wire loop. Interesting little fact here. Net force on the wire loop must be 0. So the wire loop can't change location under the action of this force. But it can change orientation. Now, doing my other picture, it looks to me like I probably should have gone into the board, but I see that the force here is that way and the force here is that way, based on what I've drawn. So although it's flipping, they're similar, but not 100%. Now, imagine this system starts to flip. What's going to happen, of course, is the wire loop is going to turn. If I'm able to maintain this current, but allow it to move, this wire loop is going to turn, but it's only going to turn until it makes it 90 degrees. If the magnetic field extends out to this location here and here, then when it makes it here, the force on that wire is still going to be this direction on the current that's up and this direction on the current that's down. So it might flip to that point, but if it passes it, the force is going to cause it to come back to where it started. So this is going to cause the wire loop to probably orient itself with the field and then stop there. Everybody understand what I'm saying? So this whole thing turns 90 degrees, gets to that point, and just oscillates until it's lined up. If I want to get this motor to flip, if I want it to be a reciprocating motor, then the moment it makes it here, what would be a good idea to have it do? Tanner? I could flip the magnetic field. That's one way of making the motor. Not ideal, because that means moving something mechanical and having that change its orientation. Aramis? Change the flow of current. That's the most likely thing to do. That's actually pretty easy to do. So if you want to make a motor, a reciprocating motor, one way is to change the flow of current at the instant you are about to pass this point. So a brushed motor does exactly that. It passes a switch that reverses the current. So the moment I make it here, suddenly the current in the loop changes direction. So this becomes into, and this becomes out of, which suddenly reverses the direction of the force on the current loop. Hopefully, the current loop has enough inertia to make it past that top dead center point right as the current flips, so that now there is a torque on the system to get it to flip again. Do you guys see that? And that is a reciprocating motor if you can keep the current flipping every time. The same way it was turning, right? I mean, as I said a minute ago, Aramis, and you gotta stick with me on these. And I know I talk fast sometimes, but anybody who's been in my mechanics class knows I'm talking pretty slow right now. I'm trying to be slower and diplomatic. And you need to, as your current loop approaches the top, like we were approaching a moment before, we need the current to change direction, but we need the loop to have enough inertia to break that plane so that there actually is a torque here. Right now, the way I've drawn it, there's no torque because the force is at an angle of 0 degrees with the torque arm. I really want to wait to cause the current to flip until just after the loop has made it past that point. So the current loop is just a little bit off, like that. Then if it flips, I'll suddenly have those forces acting in such a way as to cause it to continue to flip in the other direction. So if you're really designing the motor, you either want the current to stop for an instant as it breaks through the top, uses its own inertia to make it past that center point, and then re-engage the current to cause it to flip again. That's one way of making a motor. This allows for there to be a power stroke continuously on your motor. Of course, if you're paying really close attention to this, you realize that you develop a point of maximum force and therefore maximum torque when the motor core is aligned with the field perfectly, and that torque is diminished as you get to the edges. Like right now, there's very little torque on the motor core because this angle is small, and torque is R times F times the sine of that angle. So until I get back to 90 degrees, the torque's pretty small. There's ways around this. This is known as a single pole motor. Because of that, I only have one motor core that's actually being acted on by the magnetic field. An enterprising young engineer might realize you could wrap multiple loops, have a dual pole motor, maybe one where you have two different sets of wires being acted on at the same time, so that when one of them has minimum torque, the other one has maximum torque. Can you imagine that? That's how most electric motors are made. It does two things for you. One, it guarantees that the motor always operates in the same direction. What you might not have noticed here is the motor could operate in an opposite direction if you're not careful. It ensures that if you have your motor stuck one way, it will start in the same direction every time, even if one of the cores is lined up with the magnetic field. You can always have the other core causing it to turn. most electric motors have multiple poles to ensure they always turn in the right direction. On the other hand, the problem with this is the only way to reverse the current is to have a wire in contact with something else that's not moving. And that wire scrapes across there, making contact the whole time. But because it scrapes across it, it eventually wears the motor out because the metal contacts wear out. That's why it's called a brushed motor. We are not going to make our motor like this. It's really hard to make a motor like this the way we're going to make it. What we're going to do instead, and I need to back this up a little bit. What we're going to do instead for the motor we're going to make is when our motor makes it up to the top, we're just going to have the current turn off. So there'll be half of a flip where there's no current and half of the flip where there is. So we only get half a power stroke out of our motor. It'll still operate at several thousand RPM and it'll be effective, but it's just too hard to have the current flip. It's easier to have the current just shut off. So ours will shut the current off and then turn the current back on, and it will continuously do that. And that's what's going to cause our motor to flip. We will have to rely on our motor having inertia and enough inertia for it to turn half a flip before it's ready to receive another boost from the power stroke. But this is how you make a simple electric motor. Now, one of the questions you probably should be asking, which you might not be able to at this point, is how do you reverse the current, or how do you even stop the current? And for us, that's going to be pretty easy. And I want to show you a little bit about how we're going to do it. We're going to make our motor a little different. It's going to have a wire like this, and it's not going to be square. Ours is going to be a circle, but I'm going to stick with the square because it's easier to see what's happening. We will have multiple wraps. Now we'll probably have more like 20 wraps. I've done 1.5. You guys see that okay? And we're going to use something called enameled wire, which means our wire doesn't have a plastic casing around it. The wire's been painted. That's why it's called enameled, because they paint it with an enamel. And we will scrape the enamel off one side of the wire. That way, when we place the wire on a metal loop called the stand-ups of our motor, we'll use gravity, actually, to merely hold the motor down. And when the motor is in contact on one side, the metal on metal parts touch and we get current. And when it's in contact on the other side, the paint on metal touch and there's no current. So we're going to make motor cores in this fashion by just scraping off the paint on part of our wire. We'll probably do, though, a couple dozen wraps. And if you have any intuition at all, you realize that with every extra wrap that we have, that's another application of force. So one wire experiences a force equivalent to just a single current. If there's 20 wraps, then you get 20 times the amount of force. We're going to wrap ours in circles, though. They're not going to be square like this because we're going to use dry erase markers as the form for the size of our motor core. They're almost perfectly sized. And better yet, dry erase markers taper, so it's easy to slide the motor core off. You're going to have to learn some terminology. For example, the part of the wire that is the motor core is this, the wrapped part. And you have to tie your motor to hold the wrappings together. That's going to require somebody with a certain amount of, what's the right word here? No, although that will help. Patience. Patience. That will probably help the most. Dexterity is important, sure. And precision is important. This motor does not develop a huge amount of torque, but it does develop a huge amount of speed because we can pump it with a lot of current. And because of that, we'll get enough force to turn the loop, and it's reciprocating. Remember, it's accelerating all the time. So you will eventually reach a steady state condition where the speed of the motor is matched by the frictional torque on the core. There's very little friction, so I've seen some of these motors go 4,000 RPM. Yeah, it's pretty fast. It seems like it, but it's a tiny little motor, and it doesn't have any real power, so it probably couldn't even turn a tiny little fan for maybe an ant. It'd be like a fan for an ant. But what it will do is it'll spin really fast, and it's neat when you develop it. The problem, of course, that we're going to have is our motor cores themselves are limited in what size we can make them. And because of that, you have to make them very well balanced, meaning these wires really have to come off at the midpoints of the circle and have to cut almost a perfect diameter through the middle of the circle. If your motor is unbalanced and one side is much heavier than the other, they won't work. You're already going to have them a little unbalanced because you have to have at least half a wrapping to get to the other side, right? You see that right here. There's no way for me to come in from one side, go around once, and come out the other. I have to go around once and a half to come out the other side. But our motors are also going to be held in place by these portions of the wires. So we're going to use those as our axle to hold the motor onto its stands. You will have to build everything. You'll be building the motor core, the motor mounts, and you'll also be building the connection points that will allow current to flow to your motor. So all of it gets built by you. Tomorrow, I'm going to demonstrate the construction of